So good morning. You hear me all right? So we will start a new module this morning. It is about the physics of molecules. I think it is the only place in your whole physics BSc curriculum that deals with the physics of molecules. If you follow the development of the course, why we have atoms and then the approximation methods that we built up at the beginning of the course, and helium atoms because molecules have many electrons in general, and then the transitions, why we could have transitions between two states, and the selection rules, things like that. You will find this module of physics of molecules a very good playground to apply to what you already know. But molecular physics is slightly more complicated in that we also have internuclei interaction. That is to say, we have some internal degree of freedom inside our molecules that we need to take care of. For example, the two nuclei could vibrate and the whole molecule could rotate. That these features are absent in atoms. So we have some old physics to apply, but then we have to apply the old idea to some new features unique to molecules. If you understand this module of physics of molecules, then you are in good shape if you go into solid state physics, because solids, after all, you can think about it as a very big molecule. Okay, so let's get started. A very interesting part of the course, I would say. So I posted 2 sets of notes on this module. So if you haven't downloaded, you may go to Blackboard and then get the 2 sets. So this is part 1. It is meant to be an introduction. I would like to lay. You see me all right? You hear me? Okay, so there's some technical things here. Okay, so let me continue. So first of all, in this part, I would like to give you a very rough picture of what we will be doing. And then when 2 things bind, so here we have 2 atoms bind together to be to form a molecule, and then what we would expect, there is some potential energy profile for the binding. And then we will go into ionic bonding that we know a little bit of the physics behind it because we have done atomic physics. So we would like to do some balance sheet of energy in order to see why something binds. Part 2 is the heart of this module. It gives you basically the full picture of what is a molecular physics problem and introduce the most important approximation called the Born-Oppenheimer approximation. Okay, so that is the scope for this beginning parts of the module. So let me begin now. So it is about the physics of molecules. In particular, we will focus on the quantum mechanics of chemical bonds. We will apply Schrödinger equation, how to solve it, and then we will use perturbation theory and also variational method idea to establish that it is the distribution of electrons that would lead to chemical bonding. And then I would write down the full Hamiltonian of molecule And then we immediately realize it is very hard to solve. Well, we even couldn't solve helium atoms with 2 electrons and 1 nucleus. So we shouldn't expect we can solve H2 molecule, right? We have 2 nuclei and 2 electrons. That is even harder than the helium atom. That's true. Nobody can do the H2 molecule, which is meant to be the simplest molecule. So it's a very sad situation if you think about it. But the good news is that there are very clever approximations that we can make, and then we have a very good understanding of the physics of molecules. So what we are going to do is that we will write down a Hamiltonian of the molecule, and then we will try to approximate it into 2 parts. So basically, the technical word is that we will decouple the electronic problem, that is to say, assuming the nuclei to be fixed, not moving yet, and then solve the Schrödinger equation for the electron, and how the electrons distribute will form bonds. These bonds, as you learned in high school, can be represented by a spring. And this bond due to electrons distribution will lead to the second part of the problem that has to do with the nuclei motion. The nuclei could vibrate and the whole thing could rotate. So this is the rough idea of what we are going to do. So this is the second part. This is the first part. The first part would mean we have fixed the nuclei, and then we will try to understand the wave function of the electrons, fill electrons in by the Pauli exclusion principle, and then we will understand why is there bonding, and then what is the bond length. If you look at tables, Google, anything, oxygen, O2, what is the bond length? You will find a very concrete number. So is there any way we can understand all this by quantum mechanics? I have some technical problems I would like to solve here. Let me try it one more time. Okay. So let me move on. So at the outset, you immediately see that it is a harder problem than atoms, for the reason that we have 2 nucleus at least. By 2 nuclei, I mean we are thinking about something called diatomic molecules. But usually, say water is a triatomic molecules. We have H2O, so we have 3 things. CO2, so we have 3 atoms, and those problems are even harder. But if you understand diatomic molecules, you are in good shape to understand the other more complicated ones. Now, so for the electrons, we will be handling an electronic problem in the following sense. We have the nucleus 1 and 2, and then this shaded region is meant to be the electrons. We don't know what is the wave function. We want to solve the wave function. So you can think about it as, given the 2 nuclei in this separation, if you are the electrons, how would you distribute so that you will have a lower energy, say? All right. And after you get the wave function, you know how the electrons distribute, and then you will have the idea of bonds, chemical bonds. So this is handled by quantum mechanics. All right. Now, how can I search for the best separation, then the idea is that we can try different separations. So if the nuclei are separated by a distance, say 0.8 angstrom, it is a quantum mechanics problem. So you can solve what happened to the Schrödinger equation, fixing the nuclei as 0.8 angstrom. Then the next problem you can solve is 0.6 angstrom. Then you do it again, and then you can do it for 1.2 angstrom. Do it again, okay? So after you do it many times, the electronic energy, there will be a minimum for some particular separation called the bond length, which is the equilibrium separation. So you can think about it. We have a way to solve the problem now. I have two nuclei. I don't know what is the best separation. So I try different ways. Longer, solve the electronic wave function, find the energy. Smaller, do it again. Smaller, do it again. And smaller, do it again. And search over different separations. And then at the end, there may be one separation that the energy is the lowest. That will be a preferred separation, and that is what chemists call the bond length. 化学键的长度啊，化学键嘅長度啊。Okay, so we seem to have a way out, right? And then with this preferred separation, the electrons distribute themselves in a particular way, and that will create a potential energy minimum because that is the preferred separation, meaning force is zero. So you can imagine there is a harmonic potential around that place. Okay, and then I'm still suffering from some technical problem. Okay, did you hear me smoothly? Okay, then I go on because I am tracking myself using a different device, and it is not very smooth. Okay, then fine, no problem. I go on. Then after you have a preferred separation. So after you have a preferred separation, in classical physics, a preferred separation means it is an equilibrium point of a potential energy function. Force is zero. So around this place, the two nuclei is sensing a harmonic potential. So thereby, we will expect vibration to follow, all right? And then if you think about the molecule as two balls and the stick at this R0, the whole thing would rotate. So that is the, carry this big picture with you. We need to do three things. Different locations of the nuclei not moving yet, solve Schrödinger equation. Then we have two more quantum mechanics problems to solve. After you know how the electron distribute, then the nuclei would have a harmonic oscillator quantum mechanics problem, but you know the answer, right? And then it will have a rotational problem to solve. And last term, you also solve that. It is called a rigid rotor or rotator problem. Okay, so you know all this nice solutions. Okay, so let me move on. So the whole thing looks very complicated. However, we are quite lucky, or I would say nature has been kind to physicists, and also physicists are quite smart to explore what nature offers us. The whole problem is related to 3 different parts. So we have electrons problem, we have nuclei motion problem. But recall that the electron's mass is much smaller than the nuclei mass. A proton is 2,000 times heavier than an electron, but we are talking about oxygen or even heavier atom. So it could be 10,000 times heavier than the electron. So given this big difference in the masses between electron problem and the nuclei motion problem, you can imagine already. It's like the nuclei are, much fatter entities. Their motions is as a much a longer time scale. That is to say, slower motion of the nuclei compared with the electron mass is so small that the electrons motion is very rapid. So that will give us very different energy scales. Accompanying with that is very different time scale. So much so that I give you some order of magnitude first, and then we will justify these numbers after we solve the problem. For the electronic motions, we would expect the energy scale is of something like tens of eV. Now that is easy to understand. Just think about atom. Atom and molecules, for electrons, say, is about the same thing. What is an atom? It's an electron or electrons confined in a range of atomic size. Right? So this is atom problem, right? So hydrogen. One electron confined it to a ball radius, or times 2, the diameter. So it is 1 angstrom, right? Then it's a particle in a box problem. Therefore, h bar square over something like the mass of electron, how big the size square. This will set the energy scale of atoms. You plug an angstrom here. This is electron mass. You will get something like 10 eV. Try it if you haven't tried it, okay? But you should have tried it because it is particle in a box. All right? Now, what is a molecule? Same thing. 2 atoms, the electrons must be confined around these 2 nuclei. So the size is about an angstrom or 2 angstroms. All right? Therefore, the electron problem will set the same scale. It's about 10 eV. So it is an easy part to explain. Then we talk about nuclear vibration. This part you can imagine, it is much heavier. Therefore, it's very slowly moving. So the frequency is not very big. So the vibration h bar omega is not going to be 10 eV. It is about, at the end, we can estimate it. It is 1% of the electronic problem. So it's 0.01 times 10 eV. That's why I said here is the scale of about 0.1 eV. And then there's rotational problem. For the rotational problem, you know, usually it is angular momentum squared divided by 2 times the moment of inertia. Moment of inertia, 2 balls separated by a distance r square is the ball mass r0 square. So that is the unit for the moment of inertia, right? And then if you plug, this is the nuclear mass. So if you plug it into the denominator, and this is like h bar square in quantum mechanics, is L times L plus 1, right? So you know the rough ballpark. You plug everything in, it is again another 1%. So you see, this is 10 eV, this is 1%, this is another 1%. Another 1% will give us very nicely 0.001 eV. Okay. Now, for those who like EM waves description, the electronic energy, the scale is in the ultraviolet down to the visible range. The vibrational thing will be infrared, maybe somewhere close to the far infrared. And then the rotational one is microwave and then extend to the infrared range. That is easy to imagine. You put a glass of water into the microwave oven. 2 minutes later, it warms up. Okay, so it has to do with the rotation motion of the water molecule when you excite it in your microwave oven. It is microwave. So what I want to say here is the following. Because the electron mass is so much smaller than the nuclei mass, therefore we are lucky that we can, because the energies are very different, they are off by 1% and then another 1%, because of the difference in energy scale. Nature allows us to decouple the problem and consider them one by one, instead of a whole molecular physics problem. So this is the big picture. We will continue to justify this picture after we do more analysis, and then we have more concrete formulas to plug in some numbers. But at the outset, it is good to have this big picture to carry with you. So now let's meet some molecules. First thing first, molecules exist. Okay, apply quantum mechanics. We don't do anything that is dark energy. No one knows what it is. Well, molecules exist. Therefore, we have a very concrete problem to understand. We want to understand how quantum mechanics explains the existence of molecules and its properties. So let's meet some molecules. You know CO2, right? It is now a very, well, the bad guy of climate change. Water, also a bad guy for climate change in the form of vapor in the atmosphere. And then we have propane, interesting. And then we have benzene, and this carbon thing, organic chemistry. And then you may wonder, what does this thing mean? What is the circle in the center? Does it mean anything quantum mechanical? The answer is a big yes. If you don't know quantum mechanics, forever you only draw a circle. You don't understand what it is. And then the simpler thing we will focus on will be diatomic molecules. For example, hydrogen molecule, but that is already too difficult. We will even do a so-called molecule, but it is a molecular ion H2 plus. This is a single electron system that makes us, we can go further in our understanding of the bonding. We have oxygen, carbon monoxide, etc. But it could be also very big. So this is the famous DHA. So you must have seen many advertisements on TV, for example, good for the baby formula, make you clever, etc. So this is the big molecules. And then we have the DNA things. So we have the double helix, and then each dot is actually a big chunk of a molecule. So molecules do exist. So we have a concrete problem to try to understand. And then, first of all, realize one thing. We can probe, for example, using neutron scattering. Now, neutrons has the nice things that it does not interact with, it does not interact electromagnetically with the electrons. So it could use nuclear force to probe the position of the nuclei. And from experiments, we know that there is preferred separation, so-called bond length, between the nuclei in a molecule. So here I would like to give you some ballpark numbers so that you will not make a fool out of yourself. So here, H2, the equilibrium separation or preferred separation or bonding, whatever you call it, depending on your subject, this is 0.74 angstrom. So again, the ballpark range is 1 angstrom. Then O2, 1.2 angstrom. So the ballpark range, again, 1 angstrom, all right? Now, this is a CH4. I think it's called methane. Then there is a carbon in the middle, and then 4 hydrogen forming a tetrahedron. If you take the carbon at the center and any of the hydrogen, measure the distance between them, there is a CH bond length. It is 1.1 angstrom. Again, 1 angstrom. This is beryllium, your midterm question, right? BgH2 hydride. So it is a linear molecule. The beryllium is in the middle, 2 hydrogen at 2 sides. The equilibrium separation is 1.33 angstrom. So again, 1 angstrom, all right? Now, CO2, 1.1 angstrom. It is also a linear molecule. H2O is not linear. H2O is something like this, okay? And then we have a benzene on the plane, on the XY plane. And then the distance between a CC, is a CC bond, carbon-carbon bond, is 1.4 angstrom, all right? Now, the numbers are not, the exact numbers are not important. The important thing is have this big picture with you. Bond lengths or preferred separations between 2 nuclei are always in the ballpark of 1 to 2 angstroms. Take this with you, all right? Now, if you want to talk to the chemists or professionals, or you look up tables because of SI unit stuff, you don't see angstrom in those numbers. You will see something called picometer, 10 to the minus 12 meter. So in this unit, for example, oxygen molecule, you will find a number called 121 ppm. Okay, so it is this number. This is SI units. in chemistry books or data table, it is cited like this. But all in all, I want you to have this idea in mind, okay? Don't tell someone that, the molecule, how far is the nucleus? Then you say 50 angstrom. You will not get through any interviews, okay? Say scholarship, graduate school, you will be out. So now, there's an experimental fact now that between two nuclei, there is a preferred separation. Then next concept. So here, there's an abstract molecule that I call AB molecule. Don't take this as boron. It's just A and B is a dummy, okay? So I have a A and a B. And we know that nature will select a preferred separation, equilibrium separation. What does it mean in physics? So this page is like, think like a physicist. It means the following, right? If the distance is closer than R0, the molecule doesn't feel very comfortable. It doesn't like it. In physics, it means the energy must be higher than at R0. If you pull the nuclei to be farther apart, R bigger than R0, the molecule is again uncomfortable because the energy is higher. All right, so it means the following, right? R0 is a potential energy minimum. In either side, making it higher, bigger, is the energy goes up, smaller, the energy goes up. So we have this very famous curve for two things that bind. This is the potential energy between the two entities when they are at a separation R. The x-axis is the separation R. So from our discussion, we know the following. At the equilibrium separation, the bond length, this curve, this function has a minimum. This will be the preferred separation, R0. On either side, it goes up. So there's a minimum there. Follow me? All right. Now, very commonly, the whole curve will look like this. As the separation increases, the energy goes up, and then it flattens out. This point, when R goes to infinity, actually refers to when I have A and B atoms, they are infinitely apart. Therefore, it refers to the case before any bonding is formed. In particular, for atoms, it is important to realize that it is referring to neutral atoms far apart. Now, as they come close to each other, the electrons can think about how to distribute themselves and try to form this bond. If there is a minimum, then it means the following. Forming the molecule will gain this much energy. And that is a nice thing, right? So this is called the binding energy, B. Okay? In other words, after the molecules is formed, if you put in this much energy and try to break the two atoms, pull the atoms apart, this is the energy that you can pull the molecule apart into two neutral atoms. This is called the dissociation energy. So dissociation energy and binding energy come together. Although conceptually they are not the same, different viewpoints. Binding energy means the two things bind and then this energy is gained or given out, right? Then dissociate means I give this energy into the molecule, I try to break it, okay? So you can look up tables, again, Google, carbon monoxide, binding energy, you will get a number, okay? Again, a few eV. On the other side, if you make the two atoms too close to each other, it's not good energetically for several reasons. There is nuclear positive charge Coulomb repulsion. Repel means, you know, it goes up, right? The potential energy curve. Secondly, if you want the nuclei to be too close, the electrons has to follow. So the same number of electrons will have to live in a closer region, and you have Pauli exclusion principle that, you know, the electrons don't like to do it. Therefore, it means the energy goes up. And usually this side is rather steep. That's why you have this asymmetric curve, all right? Now, I would like, second point here, I would like you to take this picture with you. Even if you don't like more molecular physics at all, okay? You come to physics major because you don't like chemistry, all right? But you have to go through this part nonetheless. But I would like to tell you, if you like nuclear physics, this is the same curve for two nucleon that bind inside the nucleus. It's the same curve because it is the same kind of physics. So now, this is the comment I would like to make. When two things bind, usually you are expecting such a curve. This is the potential energy as a function of the separation of the two things. In nuclear physics, it will be a different scale. Now, when two nucleons comes together inside a nucleus, they need to go close to each other as much as 10 to the minus 15 meter in order to bind. So this will be Fermi. This is called 1 Fermi or femtometer. Okay, and then the binding energy is usually 10 MeV, 20 MeV, that kind of ballpark. Nonetheless, the shape is typical. Okay, so the last thing I would like you to take with you is that an estimate of the binding energy in molecule can be found very easily. So you look at this part, it must be related to something Coulombic, right? So we just plug E squared over 4 pi epsilon 0, 1 over some distance is an energy, and we plug in the equilibrium separation, 1 to 2 angstrom, okay? Then you will get a number that is a few eV. And you compare to data, this is order of magnitude is all right. Okay, so now another trick for those of you who are tired of plugging in number every time, this combination in atomic and molecular physics, a very handy number is 1.44 electron volt times nanometer. This is 10 to the minus 9 meter. Okay. If you don't like this, you are nuclear physics people, I think it's another 1.44, something like MeV, then you have a femtometer here. Okay, so now summary. In this part, I would like you to know several things. Molecules exist. Equilibrium separation, bond length, all of them is around 1 to 2 angstrom. You go into the solid state physics, you have an array of atoms forming a solid. How far apart are neighboring atoms? 1 to 2 angstrom. Okay, don't make a fool out of yourself. It's just the same kind of bonding. In a solid, the bonding just go on continuously throughout atoms. It's the same thing, all right? So then when two things bind, you are expecting a typical potential energy function curve like this, all right? And then the binding energy is something like a few eV, a few electron volt. So these are the essential numbers or ideas to carry with you. And we introduced already this. So we have bonding, we have binding energy, and then there are phenomenology of chemical bonds. In chemistry classes, you may have heard about ionic bond, covalent bond, metallic bond, all these kind of things, right? But in quantum mechanics, we will see, basically, it is related to the wave function of the electrons and what is this wave function square. So that will define how the electrons distribute in space. If the electrons tend to distribute around one nuclei more than the other, this will have one electron less. It is an anion. No, this is a cation. The electrons tend to go to the other side. This is more negative. That will be an anion. Then you say it is ionic bond. So in quantum mechanics, it has to do with the wave function and Schrödinger equation. And this ionic character or covalent character is just a matter of the solution of the Schrödinger equation. It's not preset. It is a result. So here, emphasize one more time, I show you some typical numbers of these two quantities. Bond length, again, you see 0.27 nanometer means 2.7 angstrom. So 2 angstrom, 3 maybe, okay? So you see the ballpark, 1 to 2 angstrom is about right. Binding energy, quite boring, right? 4 eV, 5 eV, 6 eV, 10 eV. So about a few eV. This group will be called ionic. We will have a better understanding of that. This group are called covalent. Again, we will discuss how quantum mechanics can be used to understand this bonding. So this I already explained. Is it ionic? Is it covalent? Is it just black and white? No. Quantum mechanics has to solve for the wave function of the electron. The square of it will tell how the electrons distribute, right? So if it goes to one A atom more, it will have an A minus, right? And leave the B plus, and then you will say it is ionic. So more often, it is ionic with some covalent character or covalent with some ionic character. And that is the real life effect. As I try to depict here, depending on the distribution, it may go to one side, then you may say that the electron like B more. So you have a B minus ion, you have an A plus ion, but it is not extreme, right? So you still have some electrons that are in the middle, things like that. You have some covalent character. It all has to do with the Schrödinger equation. Now, the next part is simple, but very educational. It is phenomenological. Phenomenological is a 為象嘅嚇，為象嘅. Before we go into the Schrödinger equation, so it is about how to balance the energy so that to achieve this binding curve. So the question is why we have ionic bond. All right. Now, we have done some preliminary preparation for this. Remember, in atomic physics, neutral atom is a quantum mechanics problem. You take away one electron, ionize the ionization energy, right? So you take away one electron, you have an ion, a sodium plus, for example, you calculate the energy again. Then you have two systems, neutral, sodium, sodium plus, you compare the energy. Then you know how much energy you need to take the electron out. That is called ionization energy. Another idea is that how fluorine P5, give it another electron, closed shell. All right, so you have a fluorine neutral atom, quantum mechanics calculation. You have a fluorine minus ion, another calculation, compare the energy. You find that F minus is actually do you am I around? Okay, all right. So now I was saying that we study the ionization energy. You need some energy to form a plus ion, and then for some system, you give it an energy, it's happier, it has a lower energy, and that is called electron affinity. Okay, so here is the idea now. Let's think about sodium chloride. Sodium atom, you have to give 5 eV in order to take the electron away. So this is called ionization energy. Okay, therefore, ionization will not occur by itself. Now, for a chlorine atom, you give it an electron, it's happier. It forms a chlorine minus, and it gives out 3.6 eV. This is called electron affinity. All right. Now, if you think about this together, will neutral sodium, neutral chlorine suddenly form sodium ion, chlorine ion? You need 5 eV. Here, it gives out 3.6. So there is a net energy required, right? That is to say, forming spontaneously sodium and chloride ion when the atoms are far apart is not energetically favorable. So that is the balance sheet. You need that to form sodium plus chlorine minus give out this, but you still need 1.5 eV. Okay, so if the ions are very far apart, this will not occur, so-called electron transfer in some chemistry language. However, once the ions are formed, there is an additional energy kicks in. It is the Coulomb attraction. Because they are opposite ions, therefore, there will be an additional term that comes in, the Coulomb, minus E squared over R. Now, depending on the separation, this negative term will carry with different weight, right? Different numbers. Will there be a distance, at least, forming the ion will break even in energy? You need 1.2 1.5 eV. But then if the separation is right, at least you gain back that energy, right? Indeed, you can equate, put it as R critical or RC, and equate it to this, you can find the break-even point. So this is the break-even point, right? You set this R to be RC and equate it to delta E is this thing, okay? In a curve, it's like this. You need this much in order to form sodium plus and chlorine minus when they are far, far away, okay? You need energy. But when they come closer, you start to gain the Coulomb attraction. At this particular distance, it's the break-even point. Okay? So we started to see there's a curve coming down. So far we have discussed this. There's a 1.5 eV required to form the ions. But for the ions, depending on the separation, there's a Coulomb attraction. Okay, so this plus this, there will be a break-even point somewhere. But now, for smaller r, as we already mentioned, there will be repulsion. Nuclear positive in charge, although the ions has a net plus, net minus, but the two nuclei start to see each other, they are repulsion. The electrons have to live very close to each other. Pauli exclusion principle also will lead to a repulsion. So this is a phenomenological thing called core repulsion energy. Now you put the three terms together. You started to see for the first time the curve that binds. Now follow my cross. My cross is here, all right? So follow my cross. You see that, okay? Now this is what we have been discussing. When things bind, there will be something like that, okay? Now once you have this, life is good to us. There's a minimum. You can read out what is the equilibrium separation, the bond length, all right? And more, you can read out the minimum energy and the zero curve. Remember, the zero here means two neutral atoms far, far apart. Not here. Here means sodium plus chlorine minus far, far apart. It is already 1.5 eV higher. You need energy to do that. So this depth here is the binding energy. Okay? So from the curve, you can read out this is 2.4 angstrom, and the binding energy to depth is about 4.2 eV. Okay? And this idea, again, confirms or justifies why we estimate the binding energy simply by the Coulomb form. You see, that comes from this Coulomb part. Okay? Now, for the first time, you see how electrons distribute, forming the ions, and the core repulsion, that is to say, the nuclei positive charge repulsion and some electron effect together will give us the typical binding curve. All right, so let me end this page and then we will have a break. This is just one page baby level or pre-baby level of covalent bond. So we talk about energetics of ionic bonds, but covalent bond, the baby picture is that, so I have atom A, this is the electron crowd, solve the atomic problem. B, electron crowd, the Schrödinger wave function problem. You bring them together, they start to overlap. Maybe the distribution, the wave function is like something like this. And if you have that, then you will have probability on finding the electrons in the middle between the two nuclei, and you call this covalent bonding. All right. Now, the question becomes how to set up the Schrödinger equation when you have two nuclei at a certain separation and you have 7 electrons, for example. You have a Schrödinger equation. How to set it up, how to analyze it, and how to at least qualitatively understand at the end, you have the wave function, something like this, and it will form a curve typical of binding. That is to say, we want a quantum mechanical explanation for this covalent bonds. That will be the topic of the second part. All right, so let's take a break now.